Alright, so today we are going to talk about a new class of functions, and before we get to them I want to talk about why we need them. So first of all, we've been working with exponential functions, right? So we have y equals 2 to the x. Well, what happens if I want to know what x value matches up with 8? So I have 8 equals 2 to the x. Well, I happen to know that 2 cubed is equal to 8, so that allows me to say, okay, well then x is 3. And the same with y equals 4 to the x, right? If I wanted to know when it was equal to 16, I would say 16 equals 4 to the x, and I know that 4 squared is equal to 16. So in this case, my x is 2. But what happens when I don't have a perfect square, right? Or so let's see, what if I wanted to know where is 2 to the x equal to 10? Well, I'm not sure, right? I know that 2 cubed is 8, and I know that 2 to the 4th is 16, so it's probably between 4 and 3, and probably closer to 3 than 4, but that's really all I can say about it. So we're going to need a new function. So that is called a logarithmic function. And it's actually the same, it's considered the same equation, it's just a different form. So let's look at the log form of things versus the exponential form of things, okay? So we'll start with, how about if we do this one right here? What if we have y equals 2 to the x? This is the exponential part of it, but it could be written as a, let me rewrite that, y equals 2 to the x. Make sure that my x looks like it's floating, right? So I don't know how to solve for my exponent when it's up in the air, essentially, when it's off the ground. So that's what logs do. So a log, we write it log, and it has a base. So this base, it's a little subscript down here, is the same as this base here, which is 2. So this is log base 2, and my equation is always equal to the exponent. So this is x. So this is saying log base 2 of y equals x. This is the exact same equation. It's just this is the log form of it. This is the exponential form of it. So this is asking me 2 to what power gives me y. Okay? So let's do, how about if I use 2 cubed equals 8. So that would look like an exponential, or this is the exponential form of it. The logarithmic would be log base 2 is my base again, right? And it's always equal to my exponent. I always think log equals exponent, right? And so then the 8 goes here. So again, this is asking me 2 to what power gives me 8, which is 3. Okay? So this is the exponential function. This is the log function that matches it. They mean the same things. Okay? So let me do one more of those with a different base. What if I had 8 squared equals, actually let me say 8 cubed equals, and let me do a smaller number, sorry. Okay, so let me do 5 cubed is 125, okay? So that means I'm going to have log base 5, because this has a base of 5, so the base is the same, and then this is equal to the exponent, so here's my 125 goes in here. So this is asking 5 to what power gives me 125, right? That's like 5 cubed equals 125. 2 cubed equals 8. 2 to the x equals y. Now another important reason that we need log functions is we have looked at things like y equals 2 to the x, and these functions, right, are one-to-one because they look like this. And if you recall the words one-to-one, essentially that means, like this is, I have a positive x base, this one means I have a negative x as my exponent. I'm sorry, I didn't mean to say base here. Or this could be 2 to a positive power, this would be 1/2 to a positive power, or 2 to a negative power. But in either case, they're one-to-one, meaning that they pass the horizontal line test, which tells me that they must have an inverse function. Okay? So that's important because if I wanted to find the inverse of this, algebraically, the first thing I always do is say, okay, well, x equals 2 to the y. I switch my x and y. Oh, oh, my y is up in the air, so how am I supposed to solve for y? So that's when we use the log form again. So we have log 2, y is what it's equal to, my exponent's always what it's equal to. So these two functions are inverses. Okay? So what if I had y equals, let me see, 5 to the x, right? Its inverse would be log base 5. It's always equal. Well, let me flip-flop my x and y here so I get x equals 5 to the y, right? So then I have base 5, it's equal to my exponent, and here's my x. So these two things are also inverses. So this helps us find inverses, solve for y when we have y as our exponent, or whenever we're trying to find our exponent. Because there's a whole bunch of great log rules that we're going to learn that help us solve all kinds of things. Alright, so I would like to point out, let's just play with the log rules a little bit longer. Okay, so let's say, let's do some more exponential forms. So I have 7 squared equals 49. I'm just going to do a couple more of these because this is kind of awkward. So that would mean I would have log base 7 equals 2. It's always equal to the exponent, 49. So if I hadn't been given the 2, this question would be asking me 7 to what power equals 49. Okay? So again, one more. 4 cubed equals 64 would give me log base 4 equals 3, and then my 64 goes in here. Okay? So this would be 4 cubed equals 64. This says 7 squared equals 49. So let's try to do some without knowing what the answer is. So for instance, what if I had the log base 2 of the cube root of 2? Okay, we want to know what is that equal to. So I'm going to think of this as log base 2 of, we'll write this as an exponent here, right? So this is the cube root of x, so the power on my 2 is 1, and then the root is 3. So this is the log base 2, 2 to the 1/3 equals x. So I can think of this as 2. What power would I have to raise 2 to get 2 to the 1/3 power? Right? It would literally be the 1/3 power. So this is equal to 1/3. Right? If I want to think of it, if I want to put this back in exponential form, I can think of it as 2 to the x, right, equals 2 to the 1/3. Well, if I have a base raised to a power and the same base raised to a power, then the powers must be equal to each other. So I get this. Okay? So let's think, okay, what's the log base 2 of 8 is how we say it, log base 2 of 8. So this is asking me, literally, I can think of this as my thing I'm trying to find as 2 to the x equals 8. Right? I don't have to rewrite it like this. I can think to myself, 2 to what power would give me 8? And that would give me x equals 3. Right? So there are some ones that we can calculate by hand. Now our calculators won't actually do log base 2 or log base 4 or anything like that. Our calculators will actually do a few logs, some common ones, and we will talk about those a little bit more in a little bit. So let me do one more that's interesting here. I have log base 2 of 1/2 equals what? Okay? So this is kind of saying 2 to what equals 1/2. Now this 1/2 I could write as 2 to the -1 power. So that would give me, so if I have 2 to a power equals 2 to the power, that means that the powers must be equal, so x equals -1. Alright. So let me just do one more mental, right? If I have log base 3 of 27, how do I figure that out? This is asking me, literally, 3 to what equals 27? And I know that 3 cubed equals 27, so that means that this is equal to 3. So 3 cubed equals 27. All right, so one thing I want to talk about briefly is that this idea of a log function is actually, we need a new domain restriction. Because, let me just think about this for a second, what if I had the log base 4 of negative 16 here, and I wanted to know what this was? Well, in exponential form, I get 4 to something here, right, my question mark, equals negative 16. Is there some power that I don't know about that I can raise 4 to that would give me negative 16, right? Because I could try 4 squared, but that gives me positive 16. And I could say, okay, well, what about 4 to the negative 2? Well, that's really 1 over 4 squared, which is 1 over 16. So anytime I'm going to raise a positive base, which all of these exponential and log are only positive bases. We all think of like the base as b. b is always greater than 1. We don't talk about them when they're a negative base, because then I wouldn't really have a function. I'd have this very odd looking thing. These are nice and smooth. That's why we like these. Okay, so but there's nothing that I can raise 4 to. If I'm raising a positive base to a power, there's no way that I can get a negative number. Also, if I tried to do this as well, the log base 4 of 0 equals something over here, that would mean I'm trying to find 4 to the x equals 0. Well, there's nothing that I can raise a positive base, and it doesn't matter if this is 4 or not. I'm just using 4 as an example. There is nothing that I can raise a positive base to that'll give me 0. In fact, if I try to use 0, that's actually 1, right? So there's nothing here that would give me 0. So our new domain restriction, right, if I had a log of x equals y, right, my domain restriction would be it can't be 0 and it can't be a negative number. So I would say that x has to be strictly greater than 0. So this is a new domain restriction. That for any log function, y equals log base b of x, right? So any base b, then my domain restriction is x has to be greater than 0. Now this makes sense because, right, this is the inverse of b to the y equals x, right? Or actually, this would actually be y equals b to the x, right? So these things are inverses of each other. And y equals b to the x, normally, right, if we think of the domain, like if I just use b as a positive base, I'm just going to use, like if this were y equals 2 to the x, actually this would be 2 to the negative x because of the way I've drawn it. So let's say that this is y equals negative 2 to the negative, y equals 2 to the negative x. I can get it out here. Okay, so if I look at this, the domain of this function is, right, it's going to go completely side to side. It's all real numbers. My range, though, stays on top of the x-axis. So my range goes from 0 to positive infinity. So our inverse here, all right, so my horizontal asymptote here becomes a vertical asymptote here, and this is what this graph looks like. And if I think about what this would mean, right, it's perfectly logical because my domain here of my inverse function would be the range here. So it would go from 0 to infinity, which this picture does, and my range would be all real numbers. I don't know why I wrote all real up here and then negative infinity to negative infinity here, but these are opposite, right? So the domain up here matches the range down here, which I could also call real numbers. I just wrote it differently. And my range up here is my domain down here. Now we haven't looked at these graphs yet, but I'm just kind of pointing out that we knew what these look like in the domain and the range of this, so it makes sense that it would be completely opposite up here. Okay? All right, so that is how we change. So just one more time, right? If I have b to the x equals y, then my log function of this same thing would be log base b equals x, and my y would go here. So these are what go together. If I had b to the y equals x, then this would be log base b x equals y. Okay, so it's b to this power equals this value. So b to this power equals this value, b to this power equals this value. All right, and the next thing we'll talk about are some common bases that we can use our calculator for.